giving me the opportunity to present my work here. And before coming to the yes, am I audible now? Yes, okay. So the title of my talk is Probing Inequivalent Form of Leggett-Garg Inequalities in Subatomic and PT Symmetric System. And okay, thank you. Before coming to the outline, I would like to thank my collaborators, my PhD mentor, Professor Alok Pan at NIT Patna, and Javed. He has recently joined this CENT, University of Warsaw, Poland, and Professor S. Banerjee at IIT Jodhpur, India. So here is a publication involved in this talk, and now this is the outline of my talk. So here I will give the brief introduction of what is microrealism and Leggett-Garg inequalities. So Leggett-Garg inequality has been derived on the assumption of microrealism to show the incompatibility between microrealism and quantum mechanics. And then we discuss this various formulation of microrealistic inequalities. So and we saw that these various formulations of microrealistic inequalities are inequivalent. And then I will discuss this inequivalent Leggett-Garg inequalities in subatomic system, and more precisely in neutrino and meson system. And then I will discuss another interesting result, that this quantum violation of LGs in PT symmetric system. And finally, I will summarize my results. So microrealism and Leggett-Garg inequalities. So the issue of microrealism is concerned with that in which limiting condition this large mass, large size, high quantum number, high dimensional system, classical results can be recovered from the quantum mechanics, or is there any boundary between the classical and quantum system? So we are certainly not concerned in which limit the mathematical structure of quantum mechanics reduces to classical mechanics, but how does the everyday world view about the nature of reality emerges from the quantum mechanics? So this question historically was posed by Schrödinger through his famous cat paradox, that when does a macroscopic system or cat stop existing as a superposition of state and become one or other state? However, Heisenberg proposed a cut, but he remained silent about this cut, that how such a cut can be obtained within the very formalism of quantum mechanics. Sorry. There are experimental approach to answer those questions, that this large organic molecules, this C60 and its compounds is show the macroscopic quantum coherence. And there are another approach within the quantum mechanics is decoherence and coarse grain measurements. So in decoherence, system interacts with the environment and leads to the classicality, wherein coarse grain measurement, by putting the constraint on the system, this classicality emerges. So, however, these attempts do not answer the fundamental question that whether microrealism is in principle compatible with quantum mechanics or not. So, this realist approach proposed by Leggett and Garg, analogous to the Bell's approach, and this is called the microrealist model. So the assumption of microrealism consists of this two main assumptions, macrorealism per se and non-invasive measurability. So macrorealism per se says that a macroscopic system which has available to it two or more macroscopically distinguishable states, that it remains in one of those states at all instant of time. And non-invasive measurability tells that the measurement doesn't affect the state itself or its subsequent dynamics. So so let us consider the simplest LG scenario of three measurements in a two-level system. Here measurement of an observable M is performed at three instant of time, say T1, T2, and T3, which in turn measurement of observable M1, M2, and M3 respectively. So from the assumption of macrorealism per se, the measurement of M should produce outcome plus or minus 1 at all instant of time. And non-invasive measurability tells that this measurement of M2 and M3 remains unaffected by the measurement, prior measurement M1 and so on. So yes. So on these two assumptions, this following inequality can be derived, which is well known Leggett-Garg inequalities, derived in this paper, where this correlation can be computed using this formula, and similarly other correlations can be computed. So now we examine the validity of this inequality, Leggett-Garg inequality in quantum scenario. For that, we consider the simplest quantum scenario, and where a two-level state is considered as this, and we take observable as sigma z, and Hamiltonian is covered by the sigma x operator, and we can obtain the observable M2 and M3 as this using this unitary evolution. And if we take this equal interval of time between the two measurements, that is this omega T2 minus T1 and omega T3 minus T2 is equal to Z, then we can find this quantum expression of this standard LGS as 2 cos G minus cos 2G. So, and if we take this, so this expression is independent of theta and phi, that is, it is independent of the state. So, and if we take G is equal to pi by 6, then it is 1.5. So, which is greater than the classical bound of this Leggett-Garg inequality. So, hence this Leggett-Garg inequality is violated in the quantum mechanics, and hence we can say that this macrorealism is incompatible with the quantum mechanics. Now, there are experimental tests of standard LGS using different physical system, electron spin, NV center, NMR, photons, and cesium atom. So now we discuss this various formulations of macrorealistic inequalities. Here is the key point that in contrast to the CHS scenario, this Arthur Fine shows that for a two measurement per party and have two outcomes of each measurement, the only relevant Bell's inequality is in the CHS form, and any other such as Wigner and CH form of inequalities reduces to the CHS one, and this SLGI often considered to be the analogous of Bell's inequality. So, but we saw that this Wigner and CH form of LGIs are not only inequivalent but also stronger than the standard LGIs. So let us discuss this formulation of this another inequality that is called the Wigner form of LGH. So satisfaction of macrorealism implies this existence of joint probabilities, and this pairwise marginal can be obtained using this joint probability using the appropriate marginalization of this measurement outcome. So, so this is one of the pairwise probability. Similarly, other pairwise probabilities can also be obtained, and using the non-negativity of the probability, we can derive this 24 Wigner form of LGS, and in the compact form, it is written in these three equations. So, so this is the Wigner form of LGS. Now we examine the, now we compare this Wigner form of LGS and Leggett-Garg inequalities. So for that, for the system we have considered earlier, this standard LGA minus 1 and 2 WLGAs are plotted against theta by taking G is equal to pi by 6. So here we can see that there is a violation of this red is for standard LGS, and these two are for Wigner form of LGS. So here we get the violation of both standard LGS and Wigner form of LGS. But if we take the other value of this parameter G, and that is G is equal to pi by 4, then we don't get the violation of standard LGA, but we get the violation of WLGA. So from here we can say that this Wigner form of LGS is stronger than the standard LGS. So now okay, sorry, I think I skipped 2 slides. So this is the comparison of Wigner form of LGS and standard LGS. So here standard LGI and WLGI both show the violation, but if we take this another value of G, then we don't get the violation of standard LGS, but we get the violation of Wigner form of LGS. So from here we can say that this Wigner form of LGS is stronger than the standard LGS. Similarly, we can this single marginal statistics for the measurement can be obtained using this marginal over this joint probability. And if we club this pairwise probability and single probability, then we can obtain this inequality. So this is 24 inequality, and we call them CH form of LGS. So yes, and again, if we compare CH form of LGS and standard LGS, then for the value of G is equal to pi by 6, we get this. We get the violation of standard LGI and CH-LGI both, but here we get for G is equal to pi by 4, we don't get the violation of standard LGI. So from here we can say that this is, CH-LGI is stronger than the standard LGI. So this is the numerical result. Now we'll see the analytical proof of this result. For that, we consider the 3-time joint probability in terms of correlation functions. So, and this pairwise probability is given by this. So here measurement, this is the disturbance created by the M1 measurement on M3, and similarly here disturbance created by the measurement M2 and M3, and here the disturbance created by the measurement M2 created by the M1 on M2 measurement. So using these pairwise probability, if you put it in this Wigner form of LGS, this expression, then we get this expression. So this is the quantum expression of standard LGI apart from these 2 terms, which may not be 0 at least from some states. Hence, we can say that this Wigner form of LGIs are stronger than the standard LGIs. Similarly, corresponding to 24 CS form of LGIs, we get this expression, that is quantum expression of standard LGI apart from these three terms. So which again may not be zero, at least from some states. Hence, we can say that the CS form of LGIs are stronger than the standard LGIs and Wigner form of LGIs. Now, I will discuss this first result, that is probing inequivalent form of LGS in subatomic system. Here we study this inequivalent form of LGS that we consider that we have discussed this Wigner and CS form of LGS in neutrino and meson system. For that, let us discuss this dynamics of neutrino system and neutral meson system. So for this three flavor scenario of neutrino oscillation, we can represent the neutrino state either in the flavor basis or in the mass basis. And this can be represented in equation 1. Here this expansion coefficient in these two representation are connected by this PMNS matrix, and this here UK alpha are the elements of the PNMS matrix. So and this PMNS matrix can be parameterized in many ways. So this is one of them, and where this Cij is equal to cos theta ij and Sij is sin theta ij, and the parameter theta ij and delta are the mixing angles and CP violating phase respectively. Now we consider this flavor state at time t0 at the and the some later time is equal to by this equation, where this UFT is the flavor evolution operator. So this is the dynamics of neutrino system in vacuum, and if we consider the matter effect, then equation this may be changed, and we will consider it in our results. So and now the dynamics of neutral meson system. So meson system is decaying in nature, and its dynamics is governed by the open quantum system. So the time evolution of the combined meson system is governed by the this unitary operator. And if we consider in the dynamics of the system, so we trace out the environmental degrees of freedom as in this equation, and we can write the reduced state in this cross operator representation. So yes, and now now we study the quantum violation of this inequivalent form of LGS in neutrino system. For that, we consider the initial neutrino state as this, and observe dichotomic operator as this. So by using this, we can get the quantum expression of standard LGS as this. So these are the P alpha beta t is the probability of transition from flavor state nu beta to nu alpha at a time t. So apart from this probability of transition, we get this non-measurable term, this beta t. So from experimental point of view, this is very difficult to it is very difficult to perform the experimental with standard LGIs. So we can bypass this non-measurable term if we consider the stationarity assumption instead of NIM assumption in the standard LGIs. But in that case, our dynamics will be more restricted. So, and interestingly, this WLGS turns out to be independent of this beta term. So, these WLGS are now independent of this non-measurable term, and experimentally this is very important. So apart from this, we can see from the plots that this the maximum violation of WLGI occur at the maximum energy of the neutrino flux. So this is the plot of neutrino 3 experiment, T2K, NOVA, and DUNE. And in all these this quantum expression of WLGI is plotted with the neutrino energy. So and in all these 3 experiments, this maximum violation of WLGI occurs at the energy around the maximum neutrino flux. So here we get the these 2 interesting features of Wigner form of LGS. Now, if you consider the this CHS LGS, then it also found to be that for these value of M1 and M2, this CHLGI is independent of this non-measurable term. And for another useful CHLGIs can be obtained for the value of this thing. And we can see from the plots that we get the violation of enhanced violation of CHLGIs. So for these 3 experiments of neutrino. And yes, and also CHLGI also show the maximum violation around the maximum neutrino flux in all these 3 experiments. Now we consider this quantum violation of inequivalent form of LGS in K-meson system. So for a K-meson system, if we consider the state as this in meson and operator as this, then with this the most suitable WLGI is found for these values of M1, M2, and M3, and CHLGI is this. So quantum expression I'm not putting it here because it was very lengthy. And so here we can see that this there is another feature of this meson system, that this blue plot is for without decoherence, and this red plot is with decoherence. So decoherence reduces the degree of violation for both the inequivalent form of LGS. And this is nicely manifested in meson system. So now I will discuss another result, that is PT symmetric evolution and maximum violation, algebraic maximum violation of LGS. So here we consider the PT symmetric Hamiltonian of the system as this, and where this gamma is the gain loss parameter, and this J is the coupling strength between these 2 level. Here J greater than gamma corresponds to the PT symmetry. J less than gamma belongs to the PT symmetry broken, and this J is equal to gamma belongs to the exceptional point respectively. So the time evolution of the state is governed by the Schrodinger equation, and it is the normalized state after the time t is given by this. Now we consider this coherence L1 norm of the so now we consider this degree of coherence in terms of L1 norm. So this is coherence can be defined in terms of off diagonal elements as this. So here this is bounded at this, and this is maximum for the maximally coherent state, and minimum for the mixed state. So for our purpose, if we consider this initial state as the maximally mixed, and then this coherence can be obtained using this formula as this. So this for alpha tends to 1, that is at the alpha approaching this exceptional point, and for large tau this coherence reaches to the maximum value. And so the coherence reaches the maximum value at the exceptional point. And if we if we consider this complementary relation between the coherence and mixedness, then so this is the formula for the mixedness, and it mixedness for the evolved state can be calculated using this formula, and it is we can see from here that if alpha tends to 1, that is it is approaching exceptional point, this maximum mixedness parameter is 0. So and it is in accordance of this complementary relation, that here at the exceptional point this coherence is maximum and mixedness is 0. So, and this maximally mixed state subjected to this PT symmetric dynamics becomes a pure state at exceptional point. So here is the plot of coherence. So at exceptional point, that is alpha is equal to 1, this coherence reaches to the maximum value. And now we see that this quantum violation of LGs in this this system. For that, if we consider this observable as if we consider observable as sigma y and state as the maximally mixed state, so the two-time correlation function can be obtained as this. And if we choose this suitable LGI for these values of M1, M2, M3, then we get the algebraic maximum violation of this WLGIs at the exceptional point, that is alpha is equal to 1, and standard LGI is also achieves the algebraic maximum at alpha is equal to 1. So this is all about this PT symmetric and quantum violation of the inequivalent form of LGI. Here I would like to mention that this result, before this work, there are two results about this PT symmetric dynamics and maximum violation of LGS using different PT symmetric system. So, but in earlier two works, it was not discussed that why it is happening. So here we provide the complete picture that this coherence is coherence reaches to the maximum value at the exceptional point, and hence and this quantum violation of standard LGI and WLGI reaches up to the algebraic maximum. So this is the conclusion, that we probe the inequivalent form of LGI in subatomic system, that is neutrino and meson system, and these inequality exhibit maximum quantum violation around the energy corresponding to the maximum neutrino flux, and decoherence is observed to reduce the degree of violation for meson system and hence non-classical nature of the system. And we studied LGIs in PT symmetric system, and this coherence is found to be maximum at exceptional point, and as a consequence this standard LGI and WLGI reaches their algebraic maximum at the exceptional point. So thank you for your attention.
Many time for questions. Anyone?
So Swati, coherence as you define that is basis dependent, right? The way as you define it, because you're just taking the absolute values of the off-diagonal terms and summing all of them.
Yes.
But this is something that's dependent on the choice of basis.
Yes.
So can you then tell us what's special about the choice of basis that you have made?
Uh,
Because I can,
Mhm.
just go into the basis of the eigenstates, and then it'll
Yes.
be diagonal, and then there will be no coherence,
Okay.
right? But you have chosen a basis whereby there seems to be some coherence,
Yes.
at least at the start. So why is that choice a preferred choice?
Okay. So, yes. Is it a question like that? Why did we choose this L1 norm of coherence? Right?
I mean, there's a quantity that is dependent on the choice of basis, and sometimes this choice is arbitrary,
Yes.
right? So the question is, why is this choice relevant in this context?
Um,
You
and-
you understand what I'm saying? I guess in some sense, if you just look at the density matrix and you wanted to say that, oh, there are some off diagonal terms and then there's some
Yes.
coherence.
Yes.
But I can also now go into a different basis.
Yes.
I mean, physically, you can think about going to a different reference frames if you like,
Yes.
for different choice of bases, and then maybe all the off diagonal terms are gone.
Yes.
Then, okay. So I mean, it's fine. Maybe if this choice of basis that you have made is somehow justifiable,
Yes.
you say that, okay, with respect to this choice, there's some coherence, but what's so special about this choice that you have made? Could you comment on that?
Okay. Mm, no, I have no comments because and so initially we have chosen this our system as the maximally mixed state, and then it leads to mm, that leads to the maximum coherence at the exceptional point.
You say maximally mixed states,
Yes.
but then there would be no off diagonal terms. I mean, they will all be zero.
Yes. Okay. Yes. Yes. That and so yes. So we have calculated this coherence of the evolved system.
Sorry, of what system?
Yes, evolved system.
Evolved system. And
Yes, means the state evolved under this PT symmetric dynamics.
mhm.
Yes.
Well, okay, maybe we can bring this
Yes.
discussion offline.
Okay.
Any other question? Okay, let's thank Swati again.
Thank you.
So the Let's Talk in the Morning will be presented by Professor Hanshen Lin.